Welcome, everyone. My name is Cynthia Pascal. I'm Senior Associate Dean for Undergraduate Education in the School of Engineering. I'd like to welcome you today to the Fall 2021 John R. and Donna S. Hall Engineering Lecture. Our speaker today is Dr. Yilu, who is the University of Tennessee Oak Ridge National Lab Governor's Chair.
So I'm very happy to be able to talk to our, we are so close to each other. I haven't been to the university too often and haven't worked with the faculty, but today I hope it will be a great beginning. I have talked to 5 faculty and I think there's a lot of things we can build from common interest, and some actually worked with my husband in the past. So very happy to share some of our work that I started at Virginia Tech and then brought over to UT and Oak Ridge. And as the title suggested, this is focusing on distribution grid synchronized measurement. Synchronized here is a time synchronized measurement. Let me see if I can move my. Okay, let's see if I can stop share and share again. That way it gave me some opportunity to move my slides a little better. Okay, see if it works. Right, very good, it worked. So we have been working, myself is working in power grid and system modeling and diagnosis of equipment failures, and my training was high voltage. So when I joined Virginia Tech, they are the, the inventors of what nowadays everybody knows in the power grid area as PMUs, phasor measurement units. Those are devices which can actually measure the angle between any arbitrary point in the grid. And that was not possible in the past because there's no high precision enough synchronization. Because the GPS receiver are able to provide extremely accurate time synchronization in a order of not just microsecond, they're nanosecond. We tested ours, it's about 50 nanosecond precision. So that becomes a possibility, and then the PMU or the phasor measurement unit were born. And the industry adopted this device and started to deploy them. They are still quite expensive. And if you wanted to get data from industry, it's extremely difficult. That's one thing. Also, some of you familiar with the power grid in the US, it's divided into 3 major ones, but if you really count all of them, and there are some smaller ones in Quebec area and the Niagara Falls area, and some not long ago was even 25 hertz or so. So we have 3 major ones you see here, and if we take Eastern as an example, which is where we all are, Tennessee, they're owned by thousands of companies. So they can actually put, this new device, phasor measurement units in their system, be able to monitor angles between substations and be able to tell the flow. However, they are not able to find information from the neighboring state, or another way to put it, neighboring utilities. So that becomes difficult to our Eastern Interconnect or West Internet or Texas operate as one unit. However, you have nobody who can see the overall performance of the grid, and you only see a piece that's your location, maybe some neighboring locations. So that's one of the motivation, along with some other interests, to observe the phenomena in the grid. There were speculations that the grid actually act like an ocean or a pond of water. So if you throw a disturbance, it's like throwing a stone in a pond, and you cause disturbance and it propagates in the system. So that's part of the motivation that we start to design low-cost devices like the one you see on the left, and change the box a few times. Now, if you hear background snoring, that's the dog. So apologize for that. So we were able to make very low cost device, design them ourselves, because it requires a much higher tolerance for noise at distribution level. So we make those boxes. We were able to send it to friends, families, universities, mostly faculty in the power grid, and sometimes radio hobby people who thought this would be interesting or cool to see the frequency in the grid. So a lot of people help, and alumni, and so they become the host of our units, and we send it all over the US, and we also send it around the world. So the yellow part is actually already orange, because Argentina already starting to plug their unit in. So we have roughly more than 300 units, and they're mostly in US, but there's probably around 50 or 60 that's distributed all over the world, because we like to know the performance of the grid worldwide, and also the places like Ireland, others are very far in terms of renewable integration. So we would like to know how they are experiencing this change and this new renewable integration. So give us a lot of information, and also when UK have their major disturbance, and they actually reach out to us to share what our measurement provide, and we help many schools who wanted to study the grid performance, and they as long as they can explain what they use the data for, we usually be able to share a chunk of the data so that they can do their research. So that's our coverage right now. So you heard me talking about, we like to know the dynamics in the grid. And what do we mean by dynamics in the grid? So whenever there's something happening, in this case, a generator tripped in Florida, and the system start to behave like a media, a continuum in response. So what you're looking at is the frequency. So the frequency is desirable to be 60 hertz, but it's never really at 60 hertz. It's always changing, and it's constantly changing around 60 hertz. And whenever you have a large disturbance, it starts to deviate quite a bit. And so this is one of a reasonably large event that gave us, and because of the monitoring system, this is an older case, 2008, that has one of the largest contingencies. So because of the distributed monitoring, we were able to see much easier, the propagation of the disturbance in the grid. And because of the time synchronization, and this, even though the system may have delay, I'm still able to piece together all the information and line up the timestamp and observe the phenomena in the power grid. And we have confirmed, yes, we do have propagation in the grid that is like what we call the electromechanical wave. So it's a lot slower than magnetic wave, but it's traveling, the speed of the electromagnetic wave, which we observe, is traveling a lot slower than the speed of light. It's like 500 miles per second or 1,000 miles per second in the Western US. The speed of light is a lot faster than that. And this is because the oscillation or the propagation was caused by interactions between generators, and those were mechanical devices that's in the system, so slow. Now, one thing we discovered is because it's a traveling wave, it has time delay. And if you look at this particular diagram, you can see I'm looking at frequency and I have them all time aligned. However, whenever an event happens, I notice there's a delay, right? And I have one red unit that see the event first, and then two others, and then so on. So this delay is what I was referring to, the propagation speed of the electromechanical waves. And that delay allow us to triangulate back the source of this event. It's sort of like earthquake. You observe at different points and you use time delay of arrival. So you can use that information to triangulate the event in terms of knowing the size and the location. And this turned out to be extremely important information for the grid operators, for NERC, for major grid operators, for reliability and balancing authorities. So this become one of the service we provide our industry. Basically, whenever something like this happen, it will automatically send out alert, and then it give you a link to show where it happened and how big is the event and what area it is. And NERC use this to actually collect their major event and to make decisions. And whenever they see a trip of more than 800 megawatt, this is quite a big plant, they would actually reach out to the location where the different reliability entities to ask them what happened. We needed the reporting for this event. So this becomes quite an interesting application for them. I mentioned when I talked to several of your faculty that actually the energy traders got interested in this, and they wanted to know what happened in order to predict the price. If there's enough of a generator offline in certain region, they know, the location or marginal price or whatever people call it could jump up. So we did a study, actually. We see the correlation, not 100%, but it's a quite a good correlation between trips, generation trips, and the price increase later on. Here's something that actually happened close to us. This is a storm that happened actually in TVA area, and 11 or 12 of their high voltage lines were out, and that caused major oscillations. And you notice that those oscillations are short-lived. They usually die down, and they're created by major disturbance, like a generator trip or something. A fault could be another reason, yeah. And so this become a reasonably effective tool in terms of observing the grid phenomena. What I show are usually, reasonably large phenomena, but we also have a lot of other phenomena that's not as dramatic as the one we saw earlier, but it's happening all the time and also start to accumulate. The frequency of those events, like the oscillation we saw here, are happening a lot more frequent, and that could become a problem when we have, the grid becomes less involved into rotating device, but more power electronics linked device, and the inertia start to decrease. So you can see here, we have observed oscillations in European grid, and this part also showing, they're actively pursuing ways to dampen the oscillation. So one of our initiative is, use the measurement and observe the grid and provide damping oscillation designs for different projects. This is one of the Italian system where we just gone through system study, and we did the hardware in the loop study. Basically, you mimicking half of the reality, and then we're moving into the pre-installation phase. Another one ongoing similar time is the New York system. We noticed that as you start to integrate more renewables in the New York area, you can start to see oscillations happening in the grid, and they are very interested in being able to figure out ways to damp the oscillations. Usually you can use fax device, you can use generators to do the damping. You can use energy storage. You can use other means, but that's something that eventually I would see more preventive measures that can actuate the damping system for grid oscillations. And similarly, we have a monitoring system installed in Saudi, and this is the work we do with EPRI to look at their system. And they also have this oscillation between the East and West, and that create not just occupies the line in terms of not being able to transfer other power, but just the power being bounced back and forth. But also they have a stability issue. Basically, if you the oscillation grow and they have to trip the line, which is really between major load and the major generation. That's crippling half of the country's infrastructure. So another one I didn't include in terms of illustration is UK. UK is a long, strip, and between Scotland and England, there's quite some oscillation going on, and they wanted to use HVDC to see if they can modulate HVDC to somehow have the power go the other way of the oscillation and then be able to control it. Okay, so what I've shown earlier were mostly oscillations that are short-lived, 20 seconds, high magnitude, but 20 seconds. You don't want them because they are usually large magnitude. They're not less fearful because they do die down when you take a band and then it dies down, and also you can damp them out. But another type of oscillation we see a lot now is forced oscillation. So you have a malfunction in your system. Let's say your governor control is malfunction. You have in this case, this is all monitored case, and this is out of our sensors. the Florida, one of the generator in Florida actually have a sensor failed. When the sensor failed, the voltage was measured to be 0. So the system shut down. And then as soon as the control was designed that when everything looks fine and they reclose and they restart. So this continuous control motion set up a forced oscillation. And usually the source is very difficult to find. And they do happen quite a lot. If you look at this page, it says a total of 12,000 oscillations detected in our case between 2013 and 2015 in the Eastern interconnection, for this large mode, large inter-area mode. So you do have a lot of those happening. We're talking about a grid with very few renewables. What would happen if there's a tremendous amount of renewables and the magnitude will go up, and you really have to have a quick way to find out the source. So one of our application basically is to be able to pinpoint the source that's causing the oscillation. And you basically take the measurement, you look at all the different areas and you piece out the phase angle of a particular mode. And then you always know the power goes from the higher angle to the lower angle. And that's also true for that particular mode. The oscillating power goes in certain direction. So you can pinpoint the source and you can take action. In the Florida case, they shut down the generator. Someone turned it off, which lasted 20 minutes actually. So we talked about generator trip. You can observe and you can pinpoint just purely by looking at your frequency. And you just plug that thing into your wall, you synchronize the time, and you have an Ethernet connection, and you're done. And the server will have the intelligence knowing all the locations. Of course, you have the GPS location of the sensors as well. And knowing the time, and they can pinpoint what happened, where it happened, in terms of generator trip and oscillation event. And besides that, there are other things going on in the grid. That doesn't go very often. In this case, we have system separation. And this power grid just fall apart into two pieces. And if the problem is not severe, usually they bring it back, in a short amount of time. So what you have seen is one is the Eastern US, one is the Western US, and you see the frequency are out together, they move around 60, and boom, one actually deviates or several deviates, and then they came back. So the system separated, they each have their own frequency, and then you can capture that and easily observe that. And this is going to be very happening quite a lot more if you have microgrid, and you have to go back to the system, you have to depart the system. So you also need to know, a lot of information for your small grid in order to have it making the connections and disconnections as well as operating it. Here's another way to look at the same problem. DOE at one point wanted to install all the units in hospitals because they needed to know in a large major disaster how many hospitals are on backup power. Because if they're on backup power, you can see the frequency. If you look at the purple line, the frequency looks quite different. Yeah. So what they can do based on that information, they would know, okay, how much fuel they still have, because the time they're on backup dictates how much longer they can last. And this is good for, FEMA and others to ration what's the next thing, which hospital is running out of fuel. That's a way to help manage the disaster. You can also see line trip, right? When the line jumped out. Usually this may not cause a generation and a load imbalance. That's why those usually don't cause a large disturbance, and it's a reasonably small disturbance. Maybe I should stop for a moment in order just realize my video is now out. So maybe easier to see a live face. Yeah. But let me stop here in case you have some quick questions or clarifying questions that audience might have. Yeah.
Sure, we do have some questions. I'm going to, being someone who knows nothing about this field, I'm going to ask a really simpler question before I get to the two that are in the Q&A. These devices, so they're small. What are they connected to? Where do they sit? Are they outdoors on some power pole? Are they at a power plant? Are they just plugged into an outlet at somebody's house? Tell us a little more about those.
Well, they have been every location you mentioned. One floated into the Katrina's water pond once. So they are designed to stay in the office. So usually we would have a faculty who put it next to his computer or desk, and they're plugged into the Ethernet. Then they plug also to his power supply, which is the 110-volt outlet. Okay. Yeah, some are in substations. We have quite a few in Egypt that's in substations. We have I'll show you a picture later on. We have, when Puerto Rico got hit, we were helping them by sending out a bunch of units, and those were in substations. Usually they are in the comm room, and then you have an antenna sticking out into outside the window, which is like a little button. They're very low cost antennas, like what you use in a car, which is a little, black piece. Yeah.
Oh,
good
great
question. Yeah.
Thank you. Well, Professor Abhishek Dubey has a question. What is the sampling frequency of the monitoring systems? Are they, well, it's multi-part. What's the sampling frequency of the monitoring systems? Are they all GPS synchronized? And how are the data stored?
Good. Right now, we have several versions. The majority of them we deployed are sampling at 1440, which means 1440 samples per second, or 24 points per cycle. We output, because the frequency we're dealing with is an electromechanical system, so the frequency are not supposed to jump real wild, right? So we only output data 10 points per second. We could output all of them, but we don't. Otherwise, we will get into the next problem, which is storage. Right now, they're stored at UT and Oak Ridge, and the older data were stored on, the jump drives. The newer data, which is within a year or two, are stored on hard disk and in our different database, SQL, or there's a company called GPA in Chattanooga. They make servers. They make, by server, I mean the software. They collect data into their database, which is a time series database. You can use DB Flash or something, they call that nature. Yeah. Now, I think I may have missed one other question.
Are the systems GPS synchronized?
Yes, that's the key. So the GPS synchronization makes it possible to observe the grid in one snapshot at a time, because once you collect the data, you send it there, you send it to the server, you're probably delayed by a few hundred milliseconds. You know, some are less, some are longer, but it's mostly within 1 second, but you do have quite a delay. So because GPS were already put in the data, every data points that's sending out, so you can piece them together automatically to have each frame from a geographic area as well. Yeah, thanks. Those are good questions. So that makes it easier for people, you know, to understand what I, you know, trying to explain in terms of applications. Yeah.
Sure.
And yeah, do we have any other questions? Yeah.
We do. I think one of them I'll probably save for the end, but this other one is, what's the main issue with oscillations in the power grid?
Aha, good question. Yeah. The small ones are usually a nuisance. It's not really of a concern. The large ones has two major concerns. One is if you have a line that carries, in the Florida example I showed you guys, we're talking about several hundred megawatt of power flowing back and forth, just continuing in the line. That took out a way useful space, right, to transmit power for real purpose. This is really just they're bouncing back and forth, not serving a real purpose. So you actually occupy the line's capacity, and that's not good. But at least that's not disastrous. But what happened is some oscillation are growing. So your system will separate for sure if you don't control it. If the system don't have enough damping, you know, then the oscillation could cause stability. So basically you break apart into pieces, the different islands, and then you start to shut down load, shut down generation, and then you have to restart. That's a long, lengthy process. Yeah, you don't want that to happen. Yeah.
Great, thank you. Do you want more questions now, or would you like to continue?
Doesn't matter. Yeah, if it's a clarification question, that's actually very useful. So it may, you know.
Okay, so then I'll throw
Yeah.
this one more, which are, what are some of the measures used for damping the oscillations?
Yeah, so the damping oscillation, so in the generator, you have a governor control. And in the energy, let's say you have an energy storage, right? And you can actually control it very fast to inject power, to absorb power. Basically, damping control is something that can quickly push power out and absorbs in the counter phase of the oscillation. That's actually a actionable and helpful process. And many fax devices, you know, many HVDC lines and synchronous condensers, those are all capable of either injecting real power, absorbing real power, or reactive power to help the grid calm down, as we call it damping.
Great, thank you.
All right, I'll continue and take more questions later on. Yeah, sorry that I didn't get the camera on. Yeah, okay. So the next thing I want to talk about is, you know, you heard me talking about inertia, because that's related to how the system react when you give a band to it, right? If it has a good large inertia, it really doesn't move much, right? If it doesn't have a large inertia, it jumps, right? So now we're having a grid that start to lose inertia gradually because renewables don't provide inertia because they are not a mechanical device. They could actually, by injecting, absorbing fast, providing, you know, you have a generator drop, you have a power loss because solar tripped. You suddenly has an imbalance between power being used and power generator. But the power electronics device, the solar or storage or wind, they can actually control the power electronics real fast and then inject power when you lost something. That act like artificial inertia. So it's not that they couldn't provide inertia in a strict sense. They cannot provide, they don't have inherent inertia mechanically, but they can provide inertia in an artificial way. So anything that stops the frequency drop in the system, it's acting like providing inertia, right? So what I'm showing here is, as we start to increase the power, don't know if you can see my mouse. So on the left, if you start increase renewables, starting, we actually created all the cases for 20, 40, 60, 80% renewable. I couldn't go any further because the system will crash. It wouldn't let me do it. I don't know how do we deal with that later on when we get to 100%, because the simulation tool becomes extremely difficult to run. But I'm pretty sure you can run at 100% renewable without major problem. So as we increase the system with renewables, you can see the inertia start to drop. You potentially could drop very low. The good thing is we have nuclear, we have hydro, so we have about 30% or 20 to 30% mechanical system that's going to stay. If all the coal, if all the gas units going to retire, and maybe people figure out a way to how to, make the gas unit clean before too late. But we always have some there, and I think we're fine in general, but we're getting to very low, right? And that actually could cause the system frequency to drop very low. You see the lines in the middle graph? Those are the lines to drop low. And the most fearful thing for the power grid, of course, they worry about blackout, but the realistic fearful thing for any CEO operating the grid is drop low, because you have a very bad publicity, you lost revenue, and also code pickup load is not, it's quite messy. So you can see that you easily get into under frequency load shedding for the ERCOT grid in the middle graph, right? And on the right side, if you get to high renewable in the 80% case, for the Western interconnection, you have to drop. You cross the line. So in this case, anytime you cross the dash line, you have to find a way to deal with it, by some artificial inertia, by some other way to deal with the problem. I didn't show Eastern interconnection because the Eastern can survive 80% without issue. However, this is just because I couldn't go very far beyond 80. The tool failed, the model failed. Doesn't mean the Eastern doesn't go all the way down. It will go down once we go up. So inertia is a very important phenomenon. So one of the a contribution or benefit having those measurements, because I measure frequency and also I measure angle. Now this is not power factor. This is not power factor angle. It's not between your real or reactive power. This is angle between two locations. This is the power angle. It determines the flow of real power. Okay, so I measure the angle, I measure frequency that allow me to be able to determine and find out system inertia. And how do I do that? If you look at the curve on the right, this is a generation trip, and usually there's some kind of oscillation go with it. This trip, the slope, you look at the red part, is a function of how big a generator tripped, as well as how big the system inertia. If I somehow figure out which generator tripped, and NERC tell us NERC always, whenever they figure out, confirm the trip, they come back to us, tell us, okay, this is which trip and where, at what megawatt. So I know the trip amount, not real time, but after fact. And then I know the inertia. I know the system inertia. So I can actually monitor the system inertia very easily with collaboration with the utility company. If we talking about real-time measurement, that's difficult because you don't have trip every minute. You don't want that to happen either. So you have about one major generator trip maybe every day or every other day. That's typical. So you don't want to, if you wanted to know your inertia every hour or every 15 minutes, you cannot do that. So you can actually monitor, you can still monitor it based on your ambient data. Now, what this is quite easy to understand is when you see a big trip, it's obvious. But power grid constantly have load turn on and off. Think about you flip off the lights. Think about a washing machine stop, right? So the load is constantly on, off, on, off. And there's many small generators that are on, off we couldn't observe. So they set up a lot of response, and being able to measure those response and give us a good hint of inertia. And this is what we are able to see. And this is the WECC system. This is comparing our measurement versus NERC data, which is based on how many generators are online. So we can actually get a very good measurement just from ambient data, just the little noise you think it's going to be, so it's a nuisance noise, but they're actually quite valuable. Now, I want you to remember the shape of this curve. You notice, this is not a fair question. Let's see. Okay, so the time start at midnight, okay, and the time end midnight. This is one day. So you notice that your inertia is very high, let's say 4 o'clock, 3 o'clock in the afternoon, right? Other times are slightly lower. You have different seasons. The heavy load season is the top, the light load season is the bottom. So remember this shape. Now you move to next graph. This is the inertia we actually observe for a small island. It's totally the opposite, right? And this is because this island is running almost 100% renewable. And in the middle of the day, there's hardly any machine on. It's all solar. So the inertia is virtually zero. And I have very good confidence we can operate a power grid with zero inertia. And this is one proof. Though it's a small island, it's operating 100% all the time. Especially during good weather, and there's quite a long time. How many hours? 5? That's almost zero inertia, and we're talking about 6 different days of the week. Their pattern are very. So this is what the grid will look like. Not to this extreme, but in larger part of US. This is a smaller island in Hawaii. So so in this case, see the inertia vary quite drastically, right? So if you wanted to be careful, you wanted to know where your inertia is, and you wanted to know how to compensate for that. And this gave you a good, situational awareness for your system. Okay, let me do a time check, and I think we're quite close time-wise. So I'm going to go faster. That way we can leave plenty time to do Q&A. Okay, so let's see. This is another example of doing what the measurement is used for. This is basically model validation. Our model in the west is a lot better. East is quite different than what a measurement is. This shouldn't be the case, right? So if you have measurement and you can use that to validate your model. You can correct your model so that you will give reliable results. We actually find out that the power grid, individual location phenomena are very nonlinear, but the large grid can behave very linearly if you have a single generator trip. So because of that, we are actually using represent the power grid as a transfer function. And because of that, we were able to have adaptive damping control where we can monitor the grid and be able to design controllers fairly easily because we're able to approximate as a linear system for small phenomena. What is a small phenomena disturbance? Even 1,000 megawatt trip generator is considered reasonably small disturbance to a grid, and the grid is very designed very easily can deal with that. Okay. For today, but not necessary for the future. So measurement give us interesting observation, and we can represent the large grid as a simple transfer function, like you would have a RLC network, or you have a op-amp, right? Another thing interesting, we have been helping the police department to somehow doing authentication for digital recording. Audio, video, all typically have power grid frequency phenomena embedded in them. So if you take an audio video signal and you do a FFT, you can extract on the left figure, you can see this is 60 hertz, 120 hertz, which is the harmonics of it. And you can extract your power grid frequency from it. And whatever grid you're in, that's what it's embedded in there. So you can use your power grid measurement. In our case, we cover worldwide. That's another purpose we wanted to see. We have a database where if someone needed to authenticate anything, we could. And so theoretically, we could take a Bin Laden tape and if that, and being able to compare. However, we don't have the database in Pakistan. So we had people asking us to authenticate the Nixon's recording. At that time, I turned it down. I said, I don't have a base case. I don't have the ground truth to compare. But now I think about it, we can actually detect truncation. We can detect sudden change. If the grid signal I'm looking at suddenly jumped from one number, here I'm talking about frequency, to another number, they're not continuous. I know there's going to be a tempering. So that's quite an interesting application phenomena. A side application for us. Let's see. Okay. So we also, we develop our hardware ourselves, algorithm, but later on we farm out the making of the device because, students don't want to do a soldering, especially the surface mount devices, too small. So we actually have been playing with the GPS reliability, and you notice in this diagram, half of the units, commercial hours, half of the units will experience GPS problem within a certain time. Like I think this may be a year or maybe 2 years. Yeah. So GPS is not totally reliable, especially during certain weather conditions. You really don't have a good GPS reception. So we are working on how to use atomic clock, some other ways to deal with it, to ride through the gaps. And people wanted to take measurement without connecting to something. So we do electric field-based measurement and the magnetic field-based measurement, because you just simply needed the antenna to pick them up, right? The rest are the same. We wanted to make the device even cheaper. We want to, see if we can just fit it into a phone, and you have the display, you have everything. So played with that. We also want to combine our device with power quality measurement, because you're doing this at the distribution level, right? So we did that. We helping, a lot of deployment in different countries, and this is in Puerto Rico, which is U.S. territory deployment. Here are, Mexico, Egypt. Where is that? Oh, Saudi and Argentina. Those are reasonably larger deployment. By larger, I mean more than 10 units usually involved. I think I come to the end of it. There's quite a number of different videos on YouTube, and some have introduction on the other work website. So I have sent Michelle this copy. So I think, Cynthia, I'd be happy to answer additional questions we have.
Great, thank you so much.
Yeah.
So the one question I deferred to later, and I still would maybe like to defer, but I want to be courteous to this person. So one person is asking, are there any current opportunities to work on projects for doctoral students specializing on high power devices? And does Ornl hire international student interns and graduates?
Oh, okay. That seemed to be answered. Yes, we do hire. We have 2 openings on field. That's the power system side, but we also hire in general international students. There are a few countries that may be difficult, Iran being one of them, but otherwise we do hire students without citizenship on F1 and other visa. We still hire people. Yeah, we
Great.
do. Yeah, Oak Ridge has a large group in power electronics. So there are 2 large groups on power electronics. One is grid related. One is vehicle transportation. The NTRC Transportation Research Center. So they should have from time to time have postings on opportunities. Yeah.
Okay, great. This question, are the ISO using the data you collect in real time, as that can help take proactive actions in exigent circumstances like wildfire and natural disasters? If not,
Yeah.
then what are the challenges?
Yeah, they could, and they could. Usually, utility operation are extremely cautious. So the reason they're not happening a lot is because we collect our data not through dedicated network, right? If you wanted to do control, you want your data source to be secured, and you also want your data path to be secured. So this one is the cyber, one is the time delay. Because we don't use dedicated communication, we are low cost operation. We use internet for data. Utility use it as a situational awareness tool, not necessarily as an action tool. However, our oscillation damping control will also ride not necessarily on our system, but on similar devices through utility. So it's very similar system. It's just the communication is the barrier for real-time use, but for situational awareness, absolutely.
Great, thank you. Another question, there are grid scale batteries in development and deployment. One example is the Ambri liquid metal battery. What effect would these batteries have on inertia?
Yeah, the batteries, if you can control them quickly, by that I mean you have to be able to catch the dropping. You remember when the frequency drops, right? You have to take action during the dropping period. And if you can take action that zone, communication should be okay. If you can, because that could take several seconds, right? If you inject power during that time, yes, you help inertia. And in the example I gave you in the island case, they solved the inertial problem by using energy storage. So whenever the frequency drops to 59.9, still quite high, right? The battery kicks in, and that is their inertia. Those are artificial inertia. Yes.
Great, thank you. Another question, are there potential sensitive security concerns with the availability of these data and small producers connected to the general grid?
That's quite an interesting question. There has always been a security concern. One example is, if someone could go into individual facility and turn on or turn off small amount of load, but okay, now I need to calm down the four-legged thing, and somehow synchronize, all the small load on and off. That could be a problem. Other than that one, I think, right now it's not that easy to penetrate a power grid because the OT and the IT are air gapped. So that means they're isolated. The operation part is isolated from the public internet system. So it's not that easy, not impossible, but not that easy to launch a cyber attack.
Well, that's encouraging.
Yeah.
And you've basically already answered another question, that is, do the devices send data over the internet?
Yes, they do. Yeah. That's another reason we don't want to use the control, because this internet could give uncertain delays. And also there's also security issue. We don't want to use it for control. So any application we develop that's worth used for control, like oscillation damping, it would go through the company dedicated communication system that way. Yeah, and we're working with companies to set up dedicated system. It can be the same sensor, but it just has to be secured.
Right. So I have a consumer level question. Many companies sell backup generators for homes, and they're supposed to be installed with appropriate transfer switches and with things that would prevent the generator from backfeeding to the grid.
Yes.
If that is not set up properly, can problems be? I mean, these generators are in the tens of kilowatts, so they're little. But could they create problems for the grid?
If they act in sync, I think they could, right? Yeah, that's
so
another
the
thing.
sync is the
because
issue.
they're too small, and they're probably problem of individual, but unlikely to be as a unified force to be big enough to cause problem for the grid. Yeah. There is one issue though, and remember, the system protection may be set up for one-way flow. So if somehow the generator is still feeding the system, not without the awareness of the distribution grid, and there could be safety issue as well, right? You think the power grid, you cut off the power, it's obvious you're out of power, but then somehow you still feeding back from the individual, which is another reason many companies install transfer trip. If you have a source, I want to be a TV, like a TV, I want to be the one actually trip it whenever I have a fault, something happened. I guarantee my personal safety.
I see. I see. Well, Professor Liu, I see no more open questions. So on behalf of all of our participants on the School of Engineering at Vanderbilt University, I just want to thank you so much for such an informative, enlightening hall lecture. Thank you so much.